Hello, everyone. Welcome back to ML Open Talk series of Yandex Hall. Good to see you here. So today we are going to talk about efficiency in machine learning, how we can utilize the recent advances in GPU technology to make training and inference of large AI models faster. And we are lucky that we have a person in the community who is actually working on those things, and we will hear from first-hand experience how to deal with 8-bit floating points. So Vlad Savinov from YandexGPT, please welcome.
Hi all. Thanks for the introduction, and really excited to be here and see many familiar faces from last month and months before. So we're going to talk about efficiency, and we're going to talk about efficiency a lot, so be ready and be prepared. This is not an easy topic to talk about, and I would really love to start by getting to know the audience, actually. So can I please ask you to raise your hand or do basically anything you want, but please be mindful of the premises, to raise your hand if you wrote any line of code over the past months, for example. Yeah, wow, so pretty much all of you. And if you trained a model, any model, like launched a training run, yeah, still pretty much everyone. And if you debugged PyTorch or TensorFlow or something similar. Oh, cool, yeah, so it seems like you're all pretty experienced with the problems, and since you've worked on this, I imagine you've seen this picture a lot, where you just sit and wait for your loss to come, right? And you think like, why is this so slow? I want to make this faster. And today this is something that we're going to talk about. We're going to talk about how to make this image into this image and how to transform your training runs so they're more like the image on the left to me and right to you. And be mindful about how to speed up your training without sacrificing the quality. And usually when you have any slowdowns in your training runs, you start thinking, how long does it take and why does it take so long? And before we actually dive deep into optimizing something, we first have to understand how to measure the time for an operation, right? And let's start with a simple matrix multiplication. So let's generate two tensors of the shapes m by n and n by k, so they can be multiplied, and just create a helper function that just multiplies these tensors and try to measure how much time this operation takes. And whenever we think about measuring time, the first idea is to just import the time library, right, and have some sort of a counter at first, then run the operation, and then have another kind of barrier. And that's exactly what we're gonna do. So we import the time library, and we have a start mark here on line 5, and then we have an end mark here on line 7. So basically what we do is we generate the data, then we run a for loop, and inside this for loop, we have a start, which is time.perf counter. This is the current time. Then we launch a matrix multiplication. Then we have another counter, and we add the difference between those two times and hope for the best, actually. And if we run this benchmark on different shapes, so let's say we run these benchmarks on matrices of shape 16 by 32, so really, really small matrices. And we also run this benchmark on matrices that are 100 times larger, we would actually get pretty identical results. And this is a bit confusing, right? Because we increased the data, shaped the data size basically by 200 times, but we still end up getting the same performance. And at this point, we probably should start thinking at least that we are doing something wrong, and this is not how we're actually supposed to benchmark the functions. And to think about and to reason about why this is incorrect, actually, this is incorrect, please don't do this. We have to take a look at how the code gets scheduled and gets executed. And we can think about it this way. So you basically have two streams of execution. The first stream is a CPU stream, where any code, Python code, PyTorch code, or anything that you've written is executed kind of sequentially from top to bottom, right? And there's also a GPU operation that has to be dispatched on a GPU and executed at some point of time. So the idea is that the code is usually structured in a way that GPU does not have to wait, sorry, the CPU does not have to wait for the GPU to finish its operation. So CPU can actually go ahead and schedule operations ahead of time. And as you can see here, so the CPU, it's this green block on top, does not actually wait for the blue operation in the bottom to finish, right? You just put it in a queue and you move on, and you do this multiple times. So what happened is we wanted to measure this block. We wanted to know how much time matrix multiplication takes, and this matrix multiplication is executed on a GPU stream, right? But what we ended up doing is we ended up measuring actually this block over here on a CPU, because we, in no point in our code did we wait for the operation to be completed, right? So there are many ways to overcome this challenge, and you can use CUDA events, you can use synchronization, but since our talk is on Triton, this is the first slide where I actually want to show you how to use the Triton, and you can just call Triton testing.doBench here on line 7, and you can just pass the function that you want to benchmark directly inside this call. And every synchronization, basically all this logic of how to wait for the GPU to finish the operation will be run internally. You can actually go ahead and see how this function is implemented. It's pretty small. It's like 50, maybe 100 lines of code with CUDA events. But this is just a one-liner that you're going to use throughout this talk to measure the time it actually takes for our operation to finish, instead of measuring the CPU time that we spent. And if we use this function now for benchmarking, you can see that the difference is pretty significant. So you can see that multiplication of matrices of 16 by 100 is nearly 8 milliseconds now, and the multiplication of small matrices is basically 0, because, I mean, they're small. And also at this point, I want to ask you and suggest that you ask your questions throughout this talk without waiting for me to finish, because the topic is actually very complicated and it's going to be much more complex with a lot of code in the future. So please, if you do have any questions at this point, maybe we can take 1 or 2 questions even at this point.
Actually, I'll ask one question. So if you're doing this on the GPU, is there any serious parallelization that would help to do both these multiplications at the same time? Like, if I believe there should be matrices of different sizes that it takes the same time to implement due to CUDA parallelization, right?
Yeah, that's a great question. So usually if you want to utilize the resources on the GPU more efficiently, you can use GPU streams, right? And you can kind of launch operations on different streams so they can be scheduled asynchronously. But in this particular case, I actually do not recommend doing this, because usually you do not want to schedule things on different streams if they compute for the shared resources. And these 2 multiplications, they do compete for the shared resources, which are streaming multiprocessors we're going to talk about later throughout this talk, or like basically compute units inside a GPU. So in this case, what you can do is, if you have like a common dimension, which unfortunately we do not have at this point, you can fuse this matrix multiplication into one kernel. So you launch only one operation and then you split the result, right? This trick is usually done inside an MLP block, for example. If you have 2 projections, you can fuse them into one projection and then just split the results, if it makes sense. Yeah, so let's go ahead then and set the goal for today's talk, which is speeding up an MLP block. And I'm pretty sure that this is something practical that you have been working with. And yeah, let's take a look at the slow MLP for now. We will just use a simple implementation without like Swigloo or mixture of experts. And if you're interested in those things, please also do explore them. They are much more complex to optimize. But in this case, let's just set up 2 linear layers. The first layer would expand the dimension by 4 times, right? So on line 6 here, we have a linear layer which takes a matrix with the dimension dim and expands it to dim by 4. And the second layer is just a down projection with the kind of shrinking the dimension back. And they also use a nonlinearity, which I think no one uses nowadays, basically, which is a GALU kernel, but it is a very nice example to take a look at. So yeah, we'll be using GALU kernel throughout. And the forward passes, we just apply a linear layer, then we run a GALU kernel, which is a nonlinearity, and run a second matrix multiplication. And so basically our goal is to try to optimize this simple function with 3 lines of code in the upcoming 50 minutes. And let's take a look at the GALU kernel we have. This is a ton approximation. It's just a lot of element-wise operations like multiplying x by x, adding a constant. Actually, nothing complicated here. We just transform the input by multiplying and summing some things up. So now, when we set what we actually wanted to speed up, let's benchmark how much time it takes now. And we do create a model here, which is a slow MLP, transfer it to CUDA, right? And have an input of shape 4000 by 4000, also located on CUDA with a D-type data type of FP32. And then we use our one-liner, which is Triton test into bench, and see that it takes 28 milliseconds. Yeah, and so what? Like basically from here, we don't know where to go, right? Because we don't know what time we expected it to run. We don't know what is the ideal time. We don't know anything. So let's try to figure this out. And to figure this out, let's benchmark the GALU kernel first. So the GALU kernel would take 2 milliseconds. So now we can kind of approximate the time for a linear layer, right? So it used to be 28 milliseconds for 2 identical layers and a nonlinearity. Nonlinearity is 2 milliseconds. So it's like 13 milliseconds per matrix multiplication. Now we at least have some sort of granularity. We know how much each operation takes, but we still do not know the ideal timings, right? And to understand, to set this goal of ideal time, we have to understand how a GPU works. And I suggest that we dive not too deep, because it's really hard to not dive up after this, but we just dive a little bit deeper to understand how to set the expectations of ours before actually speeding anything up, right? And I suggest that we think about a GPU as a combination of a compute and a memory. It's like basically a lot of compute units stick to a bunch of memory. So we can think about it this way. You have a high bandwidth memory, or DRAM, which is really big, but is really slow at the same time. Like usually if we talk about H100s, which we will be using throughout this talk as a reference, usually it is 80 gigabytes, right, of capacity where all your model weights, optimizer states, and so on and so forth are stored. And though there are things called streaming multiprocessors, so here they're marked with the SM1 and so on and so forth, SM132. And these streaming multiprocessors are independent compute units that we use to parallelize the computation and to actually perform all the operations that we care about. And inside these streaming multiprocessors, there are things called tensor cores. And tensor cores are these small compute units responsible for complex operations, such as matrix multiplication. Of course, in practice, it is a little bit more complicated. You also have a memory hierarchy here. So you, in addition to high bandwidth memory, you have L2 cache and L1 cache, which is also called a shared memory and is located on a streaming multiprocessor. And new GPU architectures are extending this idea even further. So basically, you have this memory hierarchy, which means that you can access memory a little bit faster than to always go and do a round trip to a high bandwidth memory. But still, whenever you try to estimate how long it would take you to go to an HBM and read or write something to the HBM, you should use the estimates for high bandwidth memory. And if we take a look inside of one streaming multiprocessor, then we would be able to see that there are 4 different subpartitions inside of it. And each subpartition, they're identical, those two. Each subpartition has 1 tensor core for matrix multiplications. It also has 32 CUDA cores. Again, we're talking about H100 here. And basically, these CUDA cores are used for matrix multiplications, they're used for mathematical operations, for additions, subtractions, and so on and so forth. And the tensor core is used for matrix multiplications. It is very optimized for this specific task. And if you're curious to learn more about GPUs, there is a really nice glossary I find, which is model.com GPU glossary. They have a really nice overview of modern features such as TMA, a tensor memory accelerator, and so on and so forth. But for the purpose of this talk, what we actually care about is just a tensor core and just CUDA cores that run the computation. And if we calculate, there are 132 streaming multiprocessors and 4 tensor cores inside each of these streaming multiprocessors. So approximately 500 tensor cores inside a single H100. And this slide shall tell you why a matrix multiplication is so efficient. Because essentially you can parallelize a single matrix multiplication across these 500 compute units. And these 500 compute units would be run independently and would perform a small multiplication of a small chunk of a matrix, so that as a result altogether, they would produce you a correct multiplication result for the full matrix. And if we talk about the real numbers, then we can open up an NVIDIA specification and see that it is approximately 1,000 teraflops. A flop is basically operation with a floating point number, and tera means 10 to the power of 12. So this is 1,000 trillion operations per second that can be launched in a single H100 in a specific data type. So this number is dependent on the data type that we use, and here those are the numbers for BF16. And you can also see this small star mark on the side of the slide, which says that in reality, in practice, only 80% is achievable. And this is something that we should keep in mind as well, because usually when you open up a specification, sometimes it might even say 1,800 teraflops, and we have to account for sparsity as well. And sparsity is like a feature for multiplying sparse matrices, which is not used in practice because you don't have models, at least in training, that are using this feature. So you basically have the reported teraflops, and then you also take 80%. And this is something more reliable for your calculation. So I suggest that we just use 800 teraflops per second in BF16 for the estimation. Yeah, and if we talk about memory, let's just talk about the speed of memory, so the speed of this HBM memory that we can rely on, and this is again reported to be at around 3 terabytes per second. So you can read and you can write approximately 3 terabytes of data from this really large stick of memory. And in our calculations at the team, we usually use 2.4, 2.6, something around those numbers. And now we are equipped with everything we need to know to actually estimate and run the estimation of the time it should take an MLP block to run. So we know that the input size for the GALU kernel, let's start with the GALU kernel, is 4,000 by 4,000 by 4, because the first linear layer expands the dimension by 4 times, right? So we know how many bytes it takes for the input. We just multiply it by 4 because we use FP32. Then we also multiply it by 2 because we use both input and output, and we go through the high bandwidth memory, both reading from it at first and then writing to it back. And then we have to divide it by the ideal memory speed, which is, let's use 3.3 terabytes, and we get 0.16 milliseconds. But we measured that our current implementation is basically 10 times worse. And by doing this small arithmetic, we now are able to see that this is exactly where our efforts should go into, right? So if you have something that should be 10 times faster, probably we have to try to speed this up. So let's start with the GALU kernel. Yeah, and I can see a question, so please go ahead.
I think I'll start. So you measured only time to read and write from memory, right? And
Yeah.
you don't measure the compute? Or
Yeah, that's a really nice question. So this is actually detail I made it, but in practice you should measure the compute as well. Here you can assume that your operation is memory bound. So basically you can have two types of operations, either memory bound or compute bound. A compute bound operation is the one that uses operations and calculations much more than it uses memory transfers. Here for the GLU kernel, you use approximately like 10 operations on each element, right? And on modern GPUs, in order for you to be compute bound, you have to use approximately, I'd say, 300 operations per one element to be compute bound. In reality, you can also estimate how much time it would take you to perform the computation here, but there are like no matrix multiplications, just additions and subtractions. So yeah, here we can just assume that the computation is basically free and essentially very cheap, and just estimate the memory speed. And this is actually something that you also should be cautious about, because if we kind of look into where this all is used in the distributed training setups, if you have, for example, a tensor parallelism training, then your matrix becomes very small because it gets split by the TP size, and your computation can become memory bound even for matrix multiplications, because if your matrix is very small, you actually can become memory bound, and you should also always account for the memory transfers as well.
I see, okay.
When you say by our benchmark, is this just the regular PyTorch implementation, or it's something with CUDA?
Yeah, so you're talking about unfortunately it's not close, but this is the GLU PyTorch function that we used in the beginning of the talk, right? There's a general one-liner that uses PyTorch tensors to multiply them. So this is not a CUDA kernel.
Yeah, okay, I see.
So now we know that we have to speed this up, right? And this is where Triton comes into play. And this is a very nice example to actually speed up with Triton and get to know how to use these CUDA DSLs to speed up your training. And essentially what Triton does, it allows you to write a code that would be executed directly on a GPU without touching the CUDA coding, right? So you've probably seen some kernels with .cu extensions that with a heavy C++ or C machinery, and if you don't want to go into that, you can use high-level programming concepts such as Triton to write what each block has to do. So you have these streaming multiprocessors, right? They're kind of independent. And essentially, you can tell your code what to run on each streaming multiprocessor. So you can say, okay, we have this grid of blocks, and I would assign each block to run this part of computation. And these blocks would get scheduled on a GPU in some way. We don't actually have to think about it with Triton, because Triton kind of automatically manages the scheduling. And we only have to think about how to basically partition the computation into these several blocks. And if you compare the CUDA with Triton kernel writing, then we can see that in CUDA you can control and you have control over pretty much everything. So you can control the memory coalescing, you can control all these caches that we talked about and how to use them, how to flush the data out of these caches. Triton uses and comes up with everything automatically, so you don't have to think about any memory management, basically. There is obviously a lot of downsides to this, because if you want to have a really efficient kernel, then probably you want to control how to synchronize the threads, how to memory manage, how to do all these complex things. But Triton kind of handles this complexity for you. So you get this trade-off. You would probably get an 80% efficient kernel, but with 20 lines of code, instead of getting 81% efficient kernel with 2,000 lines of code. And Triton is fully open source. You can find it here on GitHub. It was initially released by OpenAI in 2021. It's been developed extensively, actually supporting a lot of other GPU and modern GPU features. It can also be run on an AMD architecture and so on and so forth. So you can the idea is you can run the same code on different accelerators, which is really nice. Yeah, and let's take a look at the example of just summing or adding two tensors. And here's the word contiguous tensors, which means that we can assume that the data is kind of contiguously stored in memory. So if you have a tensor, a matrix, you can assume that this is actually stored as a one kind of contiguous row of data in your high bandwidth memory. So you can use pointers and move these pointers to access elements in a tensor. So imagine you have these two vectors, right? And we want to come up with a way to parallelize the computation of addition on these vectors. Let's say we cover both of these vectors with blocks. And each block independently computes the sum only with the elements that are assigned to this specific block. So in this case, block number 2 would be responsible only for summing those 4 elements and wouldn't know anything else about all the other elements, right? And now if there is a way to come up with some sort of identification for a block, so if there is a way to see like this is block number 2, then you can actually understand inside your code which elements this block is responsible for. And based on this information, you can sum only those elements. In this example, this is pretty straightforward because you don't need any sort of synchronization between the blocks and so on and so forth. But if you were to multiply matrices, for example, then the pattern becomes much more complex. And yeah, we will not go into those details today. And whenever we assign the computation to these blocks, then Triton can schedule these blocks on streaming multiprocessors, and streaming multiprocessors would run the computation for us. So basically, our programming paradigm for today is we write the code with an idea that it would be run on a small block of data, on a small chunk of data. And then we just parallelize across those blocks extensively, and the compiler, the Triton compiler, gets to schedule this computation. And yeah, let's take a look at some more code. So first we have a kind of a wrapper function, which is just a general Python function called addTensors. Basically, there are 3 parts to this function. The first is just a bunch of assertions. You can see this, for example, we check that the device placement is the same for the first and the second tensor, that their d-types match, their shapes match, and so on and so forth. Then what we do is we allocate the memory for the output inside this wrapper, so we know that the output is just storage empty of the same size that our X is. And then we launch the kernel. So the first 2 parts probably not that interesting, so let's take a look at the lines 14 and 17, where actually the core logic happens. So what we do is we have this concept of a grid, and the grid is exactly this structure of blocks shown here. So you can have a 1-dimensional grid, a 2-dimensional grid, and so on and so forth. Basically, this is kind of virtual concept for you to have coordinates for your blocks, and based on these coordinates, you would be able to understand which chunks of data to process, right? And in our case, a grid is just a 1-dimensional thing where we have x.numel, so basically the number of elements, and we just divide the number of elements by the block size. So each block would cover block size elements, for example, 32 elements. And how many blocks do we need? We need basically the number of elements divided by the block size, right? This is our grid. And then on line 17, we just launch the kernel. The kernel would be called _@kernel. We pass the grid and the arguments. So basically, the syntax is very Pythonic. You should be pretty familiar with all the concepts. Here is nothing Triton specific. It's just high-level programming, and then the Triton compiler handles everything for us. Right, and let's take a look at the actual kernel. This is where the GPU programming happens, actually. So before we used the CPU function, now let's talk about the GPU function that is scheduled and run on the GPU. First, we annotated with Triton.jit. It's a decorator that shows the Triton and kind of exposes this function to Triton so that it is able to handle it. And you have pointers, so you pass tensors as pointers. right, in memory, because tensors in the end are stored in this high bandwidth memory, just a collection of elements, and you can navigate and address these elements by having a pointer. And you also have a block size, and the block size is const expression, which shows that it should be known before the compiling time. So this is basically a constant. And the first thing that we do is we get the identifier of our block. This is just Triton.language or tl.programID, and the axis of our grid. So this would return you kind of a program ID, and you have a lot of programs. Basically, each program is this block that you scheduled. So each program can understand inside which block it is scheduled and access the elements. So we just get some sort of identifier, and in this case, these identifiers would be up to the number of elements divided by the block size. So basically on line 14 here, when we have a grid, we have this bounds, right, for blocks. And because of this bounds, we can now access coordinates here on line 4. And yeah, are there any questions?
Actually, how do you pass grid inside the function? Yes, in the square brackets. So you execute add cleaner and something magic here. How do you pass grid? Grid as element?
Yeah, so this is basically a Triton syntax. You just supposed to, if you have a kernel which is annotated by Triton
it's a decorator or Triton grid. Okay.
Yeah, exactly, and allows you to dispatch the grid passing into the kernel. Okay, let's move on then. And now, since we know the program ID, we can now understand what is the index of the element that we should start from, right? So the previous programs, they all have processed block size elements. So now we have to basically have some sort of a step of a size program ID multiplied by the block size, which would tell us the beginning of the memory, so the first element that we should start the computation from. And let's call it block start, right? So block start, we just calculate the first element we should start the computation from. And now Triton allows you to kind of program on a block level. So you have everything as a kind of a vector. And here we have a vector of offsets, and offsets are just identifiers of elements that we want to process. So here we add TL arrange, which is similar to NumPy arrange or torch arrange. It's just a vector from 0 to block size, non-inclusive, so 0, etc., block size -1. And on line 9 here we have a list of offsets that we are interested in processing. And also let's prevent an out of bounds and have a mask that would mask out the elements we are not interested in, right? Because if, let's say, we have 33 elements in a tensor and our block size is 32, it would mean that we have 2 blocks, but the second block processes only 1 element, and all the rest elements have to be masked out. Otherwise, you would read from someone else's memory and nothing is good gonna happen. Yeah, and now when we have all the offsets, we can just issue the loading instruction. So we can write Triton.load, pass these offsets, basically the element indices, pass the mask, and also there is an argument called other, which allows you to mask the elements, right? So if the elements is masked out, what to read instead of it. And this is very handy if, for example, you want to divide by y in the next line, right? So in that case, you want to pass other equals to 1, so that like essentially lets you handle, instead of if statements, it lets you handle the elements that are out of bounds. So yeah, and here we just say to Triton that it should supposed to launch a loading instruction.
So at this point, information from HBM comes to the kernel.
Yeah, it goes into the streaming multiprocessor. Yeah, so into the subpartition where we have CUDA cores and tensor cores, at this point the information is transferred directly into where the computation happens. And it can be assigned to a shared memory, to registers, or just be stored like kind of in several stages on a stream multiprocessor. And Triton handles everything for us. We don't have to think about it. At this point, we can just assume that the memory is transferred and we can run computation on top of it.
And offsets is an array, it's a list of numbers. So essentially tl.load accepts list of indices that it needs to read from HBM.
Yeah, exactly. It's like basically pointers, right? In C++, you have pointers. When you pass a tensor into the kernel, the Triton interprets this as a pointer to the first element. So when you have offsets, it's like basically how many steps are we supposed to take from this first element, and this is the element we have to read.
Cool.
Okay, yeah, and now the computation is very simple. In this case, we just add output equals x plus y, and we store the results back. This is basically our kernel. So we calculated the offsets, we ran the load from HBM, we called output equals x plus y, and we stored everything back to the output memory, to the output PTR here with the very same offsets. This is not always the case. If you're computing the matrix multiplication, you can have a two-dimensional grid where each kind of block would process like a small chunk of the original matrix, and you would have to smartly calculate the offsets. But I would just say that probably the hardest part in writing the Triton kernel is figure out the offsets and where to read the elements from and where to actually write the elements to. And this is the hardest thing probably, especially if you deal with transposes. Then you have to somehow like transpose the offsets, but the computation is usually straightforward, and Triton has a lot of built-in functions like sinus, I know multiplication, etc., that you can use out of the box. Yeah, and if we take a look at the full kernel, it's essentially it. So first we get the identifier of the block, then we read the elements, we run the computation, and we store the result back.
Can you go back? So here, this line 10 kind of assumes some memory management happening under the hood that we don't care. Like, what if this SM didn't have an additional memory to store the output? Like, this is not...
Yeah. This is basically some magic memory management happening. There are some checks that Triton would run for you, though. For example, if it runs out of shared memory, which sometimes might happen, I assume the kernel will just not compile. So there are some checks, but essentially Triton tries to, from the compiler side, to optimize it to the most efficient GPU code. And actually here I want to highlight one distinction. If you heard about TileLang or other high-level DSLs, probably you've heard that they transform the Pythonic code to the CUDA code first. Triton actually does not do that. It directly compiles the code into PTX, which is basically an assembly for CUDA. So you get the machine instructions in the end instead of getting like a C code. So there is no language transferring, you just compile directly into the GPU instructions here.
So if you have block size, shouldn't be too much. That would cause a problem.
Yeah, and we'll talk about the block size just in a second. So now when we know everything about the addition, let's focus on GALU. And GALU is basically the same thing, but now you have one vector instead of two. And you do not sum something up, you just kind of linearly transform the inputs, right? And also there are two additions on this slide, on line 3 and line 7. So on line 3, there is a special thing in new PyTorch version. So from Torch library, you can import Triton operation and rob Triton. And if you annotate your generic Python function with Triton op, this function would be kind of exposed to PyTorch through torch.ops. The namespace you highlighted and the name of a function. So here, if we set the namespace and the name of a function as you want it, now you can access your function by calling torch ops1 GALU Triton by X. And this is kind of natively imported into the Torch ecosystem. This is a very important thing to do if you're using Torch compile or Torch gtrace or something like that, because only by having this decorator, the Torch would be able to understand and to kind of see this function, right? And the second thing is just an addition to this decorator is wrap Triton. It's like basically shows PyTorch that this is where the call happens, and this is the place that launches Triton kernel. We've seen some funny examples in real world code where we forgot to use wrap Triton but use Torch gtrace. And Torch gtrace actually has a fixed branch, so it doesn't allow you to have any ifs in the code instead of Torch compile. And if you traced one code, it just stays in the same form forever. And for some reason, if there's no wrap Triton, Torch gtrace assumes that nothing happens and just doesn't launch any operation because it's not able to see the Triton call. So essentially, you have like a no-op operation in your code, which you're unaware of completely. So please do not forget to use wrap Triton and Triton op.
Maybe stupid question. What means -1 constant here? Why we use it?
Why we are basically calling x.view -1, right? Yeah, it's to be able to handle
Last element in the list?
No. It's like basically if you have like a n-dimensional tensor, you kind of view it like flatten it out as one row so that you're able to have this assumption on elements. Actually, this is a very nice question because this is not always the case. It's not always that we can run this view -1 because you have strides in PyTorch. And sometimes this stride, like the way the tensor is laid out in memory is not contiguous, so you cannot view this tensor in this fashion. This will just complicate your kernel. If you can pass the strides directly and use the strides to calculate the offsets, but here, for the sake of simplicity, we just assume that everything is stored contiguously in memory. Yeah, so let's move on with the GALU kernel, and basically line 4 to 7 is the same stuff. We just compute the program ID, do the offsets, etc., load the data. Then we launch the computation, right? On line 10 to 14, we just basically do the equivalent computation to the Python function, multiply by constants, do additions. You can also see some upcasts and downcasts. This is not very important, but here when we read the data, we upcast it to float 32. So that these element-wise operations are just more precise, so we don't lose any precision. And since we are handling a really small chunk of data, which probably resides in registers or in the shared memory, it's basically free or very cheap for us to do so. Yeah, and then we just store the result. And yeah, on the previous slide, we used a block size of 32. This was our assumption, so we just assumed that let's parallelize blocks and run 32 elements inside one block. And let's benchmark the kernel, and we would see that it is faster, indeed, but it is still really far away from the optimum. And yeah, basically the only thing that might be not well optimized is this block size. Because now we just assume that block size is supposed to be 32, that we want to parallelize across 32 elements. Actually, Triton has a mechanism called Triton Auto-Tune. It allows you to automatically explore different configurations for a kernel, and for the Triton itself to come up with the optimal configuration for your setup. And what you need to do to use that is just have a list of possible configs. Here we just pass block size from 32 to 1000, right? And you also have to have a key that would highlight and would tell Triton where it should launch this auto-tune process. So whenever the key changes, there's a new iteration of auto-tune happening. And here we just use 10 elements. So for example, whenever the size of the tensor changes, just relaunch the auto-tuning. Right? Because we assume that for a tensor with 2 elements and for a tensor with 20,000 elements, maybe the optimal block size is different, so we launch the auto-tuning. And this is the only difference between this new kernel and the previous one. We just have this decorator. And now if we benchmark the kernel, it is now 0.18 milliseconds from the optimum, which was around 0.16, I think. So this is very close to the ideal time, right? And this is the place to stop and be happy about a speed up, but focus on matrix multiplications because they are still slow. And let's pause for the questions here.
Do I get it correct that when you do the auto-tuning, it just runs different kernel sizes and then choose the minimum one, or how it works?
Yeah, basically the process is very similar. There is one caveat that you should be careful about, right? If you use different shapes throughout your training, like you use different batches, this is a very tricky thing to write because it would just compile the kernel multiple times and you would see every iteration being slow. Because essentially this compilation and the running process, the choice of the minimum time would happen on every iteration. But if you have fixed shapes, this is the cost that probably you are willing to pay because you just run this auto-tuning process, store the results in cache, and the actually optimal kernels are stored in a special Triton cache by this key that we provide here. And then you just access the optimized kernel for the rest of your training run.
So 0.18 that we see is the optimal out of all this, but in general, it ran everything for our test.
Yeah, that's true.
When we take a Triton kernel from somebody else, I mean, ready to use, I don't know, do they have that auto-tune under the hood already? Do they use all the same trick?
Usually yes, and this is very problematic because if you use different shapes throughout your training, probably you do not want to have this auto-tuning process. Usually whenever we use different shapes, we run this similarly auto-tuning process in Jupyter notebook, right? You select the optimal configuration and then use it for the rest of your training. But if you import the library, it may actually use Triton auto-tuning, and you would have to deal with this secret by yourself.
So does it return what was the optimal one?
Yeah, you can get this idea. It does not return it out of the box, but there's an option for you to get the optimal configuration.
If I know the best value for Triton, may I assume the best value for C++ code or something with CUDA native?
Probably not. You can explore the PTX though, if you're very curious. But I'd say this is the best thing you can get because this block size is essentially a Triton concept, right? It is in C++ you would control everything from the thread level, and you would probably not get this block scheduling at least out of the box in CUDA. Yeah, I suggest we move on.
Yep.
And the question we can ask now is, why did this happen, right? So we had a slow code, now we have a faster code, but we do not understand where the slowdown came from. And this is another important question to ask. And to get this right, we have to profile the run. So there is a profiler built in with PyTorch. You can use it with storage.profiler.profile here on line 10. And you can pass a lot of different arguments to it. For example, the most important ones are just activities. Activities is a list of accelerators, in this case CPU and a GPU, that you want to see the traces and the actual functions that are being launched. And there are some other arguments, such as whether you want to take a look at the stack trace, etc., etc. And to use the profiler, you just use this context manager and then call your regular function, right? And if you profile the alt GLU kernel, we would see something like that, which would look pretty terrible, I'd say. So let's try to figure out what's happening here. So on top, you have a CPU stream. And the CPU stream is where everything is getting launched from Python. You can see Python overhead by yourself. It's just huge. I ran it from IPython. So there are a lot of dynamically executed functions here. But what's happening is just this small kernel, A10, multiplication it just launches and gets dispatched to a GPU. So like basically on top you have what's happening with your Python code. And usually you're not really interested in these things because you can just assume Python is slow, but Python schedules everything on the GPU beforehand. So let's focus on the GPU stream. And the GPU stream is something underneath, right? And you can see a lot of these colored blocks, wait at native something something. Those are actual GPU kernels. So whenever you run your PyTorch code, it executes pre-written CUDA kernels. So whenever you multiply by a constant, whenever you add something, you have a kernel such as multiply or add or compute flash attention or something like that. And all these separate kernels, you would be able to see them here on the GPU stream, right, and explore what actually happens. So let's remember the GALU kernel. We kind of were hoping that we would get just one kernel out of GALU, right? We would just have all the multiplications and summations happening in one place. But here we have this like huge colored sausage of kernels where we just multiply, then we add something. And what happens is every time we do this, we take the data from HBM, we load it internally, we add one constant, we write it back to an HBM, then we read it again, we multiply it by a constant, and we write it back. And we do this 10 times. So for all the GALU operations that we had, a single new kernel was launched. And because the memory read was our bottleneck, right? The memory access is very slow. Essentially, we accessed memory 10 times more than we needed. And that's where our 10 times slowdown came from. So essentially, our kernel did not manage memory correctly. And now with Triton, what happened is we just read everything at once, we run all the computations at once, and we write it back. So if we were to profile this, we would see only one kernel being launched. And obviously, this would be much faster. Yeah, let's move on. Yeah, now we can speed up matrix multiplications, and to speed up matrix multiplications, we have to talk about lower precision, and unfortunately, we've spent quite a bit of time on the kernels, but let's try to speed up matrix multiplications a little bit. So the idea we are curious about is we had data in FP32. Right? And FP32 is a D-type which has 32 bits for one element. We can just cast it to BF16, and if we cast something to BF16, we can see basically a 2 times speed up, because tensor cores are optimized to launch computation on smaller D-types and launch this computation much faster. So we can actually compute as well the ideal time for the matrix multiplication. To do this, we can just count the number of elements we would write back, basically the number of operations we would have to do, and we know the ideal number of operations our GPU can run per second. So based on these numbers, we can arrive at the estimation that our matrix multiplication is working at approximately 700 teraflops, which is really close to the optimal numbers, right? The optimal numbers are 990. And here are 700. So probably with matrix multiplications, we wouldn't be able to have this streak as such as we did with Triton, where we just write a more efficient kernel, and we are happy to go, because for matrix multiplications, libraries such as Catlas or Cabolas, they already have efficient implementation, and PyTorch uses them by default. So yeah, it's nearly impossible to speed up our code by optimizing the kernel. And basically the only way to speed up our matrix multiplications is to leverage a lower precision. So for lower precision, yeah, probably this is not a lot of useful information, but for lower precision, we can have several bits split between mantissa and exponent, right, between exponent and fraction, which highlights how precise and how large our number is. And whenever we use the smaller number of bits, it means that we can run the computation a bit faster. And if we take a look at the specification from NVIDIA, we can see that for FP8, here in the lowest row, it's basically 2 times faster than in BF16. So by going from BF16 to FP8, we are able to get basically 2x speed up, right? And this is something that we have to be curious about. But the problem is that these numbers lie in a really small range. So FP8 numbers are basically between -400 and 400, And that's not a lot of useful computations we can do with numbers between -400 and 400, because usually your activations, your gradients are very large. So there has to be a way to transform the number from BF16 to FP8. And whenever we figure out this way a bit later, we can leverage this fact that if we are able to view our matrix as BF16 is FP8 matrix multiplied by some scale, so by some correcting factor, and if B matrix can also be viewed this way, then the ABF16 by BBF16 multiplication can be transformed into first multiplying the FP8 matrices and then scaling this result by the combination of scales. Yeah.
1 second. So here the important part is that this matrix multiplication part is the heavy part, and that can happen in tensor core, and this scaling is element-wise multiplication,
Exactly.
which is what we just optimized in.
Yeah.
Okay.
Exactly. So when we view our matrix multiplication this way, we can now leverage tensor cores to multiply matrices in FP8, which would be much faster, and then just scale the result by the scales, right? And the only thing we are...
But actually, how we choose I-scale and B-scale values?
Yeah, let's take a look at the few next slides. So why should we care about this stuff is if we take a look at the adoption on FP8 formats, so everyone trained with FP32 long before, right? Then transformed to FP16, then to BF16, and you can see this slow growth of yellow blocks with FP8. And I assume that this growth would continue as many more GPUs would get released. So I think that the world's gonna adopt the FP8 training. So it's very, it's the right time to think about how to train our models. Yeah, and when it comes to the scaling part, basically what we wanna do is we wanna scale the tensor from tensor max and tensor mean to the distribution, the tensor mean to tensor max to -400 and 400, right? So we have some sort of a distribution of our elements, and we want to move this distribution to the desired distribution in FP8. The easiest way to do this is to just find the absolute maximum in a tensor, divide by this absolute maximum, and multiply by 448. Doing this operation, you would end up getting the tensor that lies in the correct range. But this is a bit problematic, because first, we would have to cast to the FP8 type and lose some precision. And second, obviously, there might be some outliers, right? If our tensor is very large, it's an activation matrix of like 16,000 by 16,000, we would obviously get some outliers. That would become this absolute maximum, and everything would be pushed closer to a zero. And near the zero, actually, the grid for FP8 is not that precise, so we would lose some precision. And if we take a look at this operation, imagine you have a BF16 tensor. The absolute maximum is 1,000. So you find this maximum, you divide by it. Then you scale by by 448, and you have this tensor, and then you cast. So when you cast, you basically take the closest FP8 point to your BF16 point, and round up or down towards that. And by doing this, you lose some precision. So if the result of the operations beforehand is 44.8, now it's just 44. If it's 13.44, now it's 13. So you lose a lot of precision, actually, right? And you have to, because of that, the quantization, which is the operation of transforming BF16 to FP8, is kind of not reversible. So you cannot take the FP8 result and go back to BF16, right? You would still end up getting this error accumulated. And yeah, there are a lot of models that's been released with this training paradigm, such as Llama 4, where they say that they use it for efficiency but do not share anything else. An Ematron model by NVIDIA, which is a hybrid model with Mamba layers, and they witnessed some loss degradations, but the benchmarks were the same, and the benchmarks on math and code actually were better, which is a bit unexpected, but several papers report this. So yeah, sometimes wonderful things can happen. Yeah, there are like a lot of different findings of how the losses look when you train with BF16 FP8, but the important thing here is if we take a look at this model, which is command A in the previous model, you can see that they use some sort of regularization. So here they used the BF16 warm-up. In the previous model, they used the first 4 layers and the last 4 layers in BF16, because training the full model in FP8 is very challenging because of this outlier. So you have to use some operations in BF16 still. Yeah, unfortunately, it is very unstable. But then DeepSeek came into play. Yeah, and probably we can spend like the rest 5 minutes talking about DeepSeek, and then you would have the floor for questions, and you can go enjoy the after party afterwards. So the DeepSeek uses a very nice trick where we actually use block quantization. So instead of computing the scales inside one matrix, right, and having a really large matrix with a lot of possibilities for outliers, we can compute a scale inside a block. And if you compute a scale inside a 100 by 100 block, probably even if this block is scaled like faulty incorrectly, it wouldn't have a lot of effect on the end-to-end training, right? So now when we do this A scale and B scale that we discussed is also a matrix now. It is not just a single scalar, it's also a matrix of these scales. And you can have the same for activations, and for activations they use these rows of 1 by 128, and you compute and scale all of these blocks kind of independently. And whenever you do this, now you have to be able to multiply the FP8 type and a matrix of scales to, again, a weight in FP8 and a matrix of scales for the weight. And basically there is no known way to do this efficiently, so throughout the open source week that happened last year, DeepSeek also open sourced a library called DeepGam, which is available on GitHub. This is a very terrifying image, but actually what happens is here on top we have activations, which are quantized in tiles, and you have weights, and you can read one tile for activations, one block for weight, and corresponding scales. And just process one tile, one block, and one number for scales, and multiply them efficiently inside a GPU. And this library is like available on GitHub. You can go and use it. And yeah, there are some rules that DeepSeek follows as well, which is like balancing the computational D-types between the forward and backward passes, using FP32 for accumulations, storing gradients in FP32, storing master weights in FP32. But basically the recipe is we just quantize everything to FP8, run the computation, and then dequantize it back, essentially like that. And by doing so, we can run the matrix matmulls in FP8 and have a very fast training. Yeah, and obviously to implement this quantization, we can use Triton. And actually, there is a course happening right this week, which is LLM Scaling Week, run by me and my colleagues from my team. It is unfortunately or fortunately in Russian, so you can go ahead and register. There are a bunch of YouTube videos on that we explore also how to actually write these quantization kernels and how networking works, how arithmetic for large-scale training works. So if you want further details on like the low-level stuff, please go ahead. We spent a lot of efforts and invested a lot of effort into making this course alive. And yeah, we can just write the linear layer, or we can use libraries available on GitHub, which is Transformer Engine or PyTorch AO, which provide you with these quantization kernels and matrix multiplication kernels for FP8. And if we do this, we are able to get basically a 4 times speed up for linear layers compared to FP32. And this is it for today. So I really want to highlight the 4 things from this talk, which is first, please measure the right thing, right? You are really curious about the GPU time and not the CPU time. So leverage Triton testing to bench, CUDA events or something else to first understand how long your code, your single function takes to run. Once you understood it, please run back of the envelope calculation to arrive at like the ideal estimation. If your code is 5% slower, maybe there's no need in investing your time to speeding up. But if your code is 10 times slower, probably it would be a good place to start. Then profile the results and actually take a look at the visual traces and see what happens inside your computation, why your kernels are slow, why your code is slow. And only when you understand why something is slow, then go for Torch compile that can generate Triton kernels automatically for you, or go for Triton and play with lower precision. Yeah, and please, if this talk was helpful and you actually achieved speed up, shoot me a message. And I'd be really happy to hear about that, because in the end, this is why we are here. And use this feedback form to leave the feedback on the talk. Thank you.
Time for questions. Thanks a lot.
Thank you. So when we are speaking about this quantization, is there any big lab or like big companies that did the training in FP32, FP16, FP8, and then had the comparison of, I mean, the big models, that the ones that are expensive, and say that, okay, we don't lose much here?
One such company is Yandex, and yeah, for example, we in our team, we ran over the past a lot of months, a lot of experiments with the FP8 training, and we plan to share a bit more in the upcoming future. But essentially, if you're looking for public reports, there is a DeepSeek model, and there are like some other models I highlighted here which use FP8 and observe basically no loss in precision. In our internal testings, usually if you work with dense models and with pretty small models, like up to 7 billion of parameters, so like 30 billion of parameters, small models nowadays are 30 billion of parameters, right? You can even go ahead and use a per tensor quantization with just one scale per tensor, and probably it would not affect your quality. But if you're working with mixture of experts or with models that are pushing towards like 100 billion parameters or 50 billion parameters, there are even public reports I mentioned here that complain about FP8 per tensor, but the block-wise recipe suggested by DeepSeek, and actually it is natively supported on modern GPUs now, which is MX FP8. So if you happen to have a couple of Blackwell GPUs, you can, not even write the quantization code. You can just leverage the built-in instructions for all of this, essentially. But yeah, block-wise recipes are pretty stable even at large scales.
Hi, thank you for the talk. You showed a slide where different precisions were used for different purposes, like layer normalization or matrix multiplication. How do people decide what to use for what purposes? Is there a systematic way, or they just try, it works or it doesn't, and they stick with the lowest memory option that works?
Yeah, essentially, since we now have a field which is kind of alchemistry, you try and see what works and not. But if we think about it, like if I ask you, would you run a softmax operation in FP8? Yeah, probably not, right? I mean, if there is a division, probably you don't want to do that. And the rule of thumb is you want to run matrix multiplications in FP8 because this is the part you can benefit from the most. And other operations such as normalization, softmaxes, all this small stuff like RMS norm that uses some sort of division or scaling or requires really fine-grained precision, probably just not worth the effort, and they don't account for many floating point operations in your training anyway, right? So usually the rule of thumb is use these operations in FP32 and or in BF16 and only use matrix multiplications in FP8.
What different profiling tools can we use or for instead of torch profile? For example, something like full stack profiling, full stack traces without any instrumentation.
Yeah, so essentially, if you're using PyTorch, there's just this context manager. There are also native profiling tools by NVIDIA, and site profiler, NSU, and so on and so forth. Usually, personally, I do not use them because the traces are 10 gigabytes and my laptop is just flying to the outer space when I try to open it up. With torch profiling, it's usually like 1 gigabyte maximum. But if you really want to like the detailed view of each GPU stream, of the number of stream multiprocessors that have been used when the operation is scheduled, I suggest you explore the instruments provided for free by NVIDIA. And if you are using JAX or TensorFlow or Keras, I'm pretty sure that those frameworks should have some sort of a native profiling as well. Yeah, and probably this should be something similar to PyTorch.
This Torch AO or whatever that you showed in the last slide, does it implement the DeepSeek style block level quantization?
Yeah, essentially, I think the DeepSeek block style quantization is implemented efficiently only in Transformer Engine at this point. However, in Torch AO, there is a row-wise and column-wise recipe which uses the full column or full row for quantization, which is also pretty similar to the block style, right? But the one thing to be careful about when using the Torch AO, since it's a native Torch ecosystem, it relies heavily on Torch compile. So it's no stranger to writing the quantization code in pure PyTorch and relying on you to compile the training run. So this PyTorch code would be transformed into an efficient Triton kernel. Sometimes this wouldn't happen, and sometimes you would just get a lot of like for loops happening to quantize the tensor, something like that. But usually if you use Torch compile in your training runs, Torch AO with column-wise and rows, I think should be pretty stable, but we did not use it and we wrote the recipe from
And
scratch.
this deep gem is usable, or it's... I didn't understand the relationship between deep gem and Torch AO and Transformer Engine.
Yeah, so basically there are multiple ways you can actually write the kernel, right? So you need the quantization strategy and you need the matrix multiplication. And depending on which quantization strategy you use, you have to have a different matrix multiplication strategy. So either to accept a matrix and a single scale or a matrix and a matrix of scales, right? So the library by DeepSeek, which they open sourced, is a specific library only for matrix multiplications, only for the format of block-wise quantization by DeepSeek. In Transform Engine, they rely on Cutlass, and in Cutlass there are also now kernels, but if we benchmark them against the DeepSeek's implementation, sometimes they're faster, sometimes they're slower, so depending on the use case, there are multiple solutions.
I see. I have one more question about this concept called MFU, mean flop utilization. So I want to understand how all of this is connected to that. So if you took this GELU optimized at different levels, right? So the first, we had 3 options, right? Non-optimization, Triton with a guessed block size, and then the auto-tune. If you actually run this and then compute MFU, will it show the same difference as this time differences?
Yeah, that's a great question as well. So another metric that is very similar to MFU is a tensor core utilization. Essentially, if you pay for a GPU, you want to use as many compute units as possible, right? And to be as much compute bound as possible. So if your time is wasted on communications a lot, probably this is not something you want. And these kernels, such as GELU, they produce a lot of memory-bound operations. And whenever you launch memory-bound operations, your tensor cores are not utilized. So if you take a look at the tensor core activity, with the first implementation of a GELU kernel, you would see significantly lower results versus the tensor core activity for the second kernel because of the memory overhead, right? The memory overhead becomes smaller, so the tensor core activity increases. MFU is a concept which allows you to basically estimate the number of flops you can achieve in the perfect and ideal world, but when you use the mixed precision training, some operations on a BF16, some operations are FP32, some are FP8, there are still debates on how to measure the MFU correctly, but there are no debates on how to measure the tensor core activity, so you can take a look at those.
Okay, do we have more questions?
Have you had any experience with floating point 4, FP4 trainings?
Yeah, so I would say, unfortunately, not all the questions can be answered from my side at this point, but there are some recipes in FP4. There is a report by NVIDIA which tried to train an FP4 recently, and actually our colleagues at Yandex Research in collaboration with some Austrian universities are exploring the kind of post-training methods in FP4. There are some promising results, but the FP8 has been introduced, I think, 2 or 3 years ago. And only this year we started seeing open source releases that actually use FP8, right? So I think there are definitely a little bit more time needed for us to see full-scale large model fully trained in FP4. But yeah, hopefully there are some people who explore this more deeply.
Thank you.
More questions? Okay, I think we can thank you again